Section 16.3 starts on page 989, talks about path independence, a big deal for us. Conservative vector fields, those are simple to verify. I'll show you what that means. And potential functions, another important topic. Those are three things that we're going to use. And let me start with a definition. It says, let F is a vector field, of course, be a vector field defined on an open region D in space. And suppose that for any 2 points A and B in D in the domain, this integral of f dot dr, which is what we've been doing all along, in the previous section and the section before, circulation. It has so many different names. Along the path C from A to B in D is the same over all path from A to B. Then the line integral, this integral, is path independent and the vector field is conservative. So if we have a conservative vector field, it doesn't matter which path you go along a curve C from point A to point B. All of these would be the same. And an easy way of checking if you have a conservative vector field is by taking del crossed with F and see if you get the zero vector. Now, I don't know if you guys read the book. If you do read the book, they have a lot of definitions. I'm only picking 3 of them, the only ones we need. And we're going to proceed, and that's all I'm going to use. And the word conservative, I just thought it would be a nice note to show you. The word conservative comes from physics, and they're talking about the principle of conservation of energy, right? So, in case this ever comes up, this has another word in differential equations. If you have an exact differential equation, that's when the gradient crossed with f equals 0 as well. Has a lot of applications, extremely useful. For now, we're going to apply that. Just look at that. And if you read the book, you got to follow the definitions if you want, or you could use this definition. I think this is much simpler, but that's only me. So on numbers 1 through 6 on page 998, it says, on 1 through 6, determine which fields are conservative. For now, we make a big fuss about that. Later on, we kind of drop that. If it is conservative, it has certain applications, but if it's not conservative, that doesn't mean it cannot be done. You can still do it. So if I want to figure out if it's conservative, I'm going to stick with what I mentioned. I'm going to take del crossed with f. That is I, j, k. Del is the partial with respect to x, the partial with respect to y, and the partial with respect to z. Basically the cross product. This is y, the sine of z, and this is x, the sine of z, and this is xy, the cosine of z, and that would be the I component. If I want to look at the I component, I would cross the partial with respect to y is x cosine of z minus the partial with respect to z is x cosine of z. If I want to figure out the j component, that always picks a negative, and I'll take the partial with respect to x, that's y cosine of z, minus partial with respect to z, y cosine of z. So far, it seems I'm on the right track. If I notice automatically that that's not a 0, or one of them is not a 0, I stop. I'll say, hey, it's not conservative. And if I go for the j component, for the k component, cross its row and column, and that will be the partial with respect to x, that is the sine of z, minus the partial with respect to y, that is the sine of z, and that's 0. So basically, I got the 0 vector. Let me not mess that up. Let me make that nice. So therefore, it is conservative. And did I give you a, yeah, I did that vector. Good. And on number 4, I wanted to do it 2 dimensions. You have 2 options when you want to take the gradient crossed with f. If it's a 2 by 2, now you could do this if you want. You could say partial with respect to x, partial with respect to y, partial with respect to z. Now, you could do that just in the beginning. And you could say that's a negative y, that's an x, and that's a 0. But that's going to always give a 0, and that's useless. So you could just do literally this. That'll work. And we know how to do that. The partial with respect to x is a 1 minus the partial with respect to y is a negative 1. That's 2, which does not equal 0. Therefore, not conservative. Now, the reason they check for conservative is for the next part, and I'll elaborate on that in a minute. Another definition says, if f is a vector field defined on D and the vector field is some gradient applied on some function for some scalar of f on D, then f is called, this f of x, y, z is called a potential function of f. Now, if f is a vector, f is a conservative vector field, and you find this function has specific properties. Here in this book, they're just saying, you know what? Just find us a potential. What does that mean? This means M, N, and I forgot what was the last thing they called it, but they had it in order. They called them M, N, and P. That is F. Equals the gradient applied on f. Isn't that f sub x, f sub y, f sub z? So this is what they want. They want to find f of x, y, z such that when you take the gradient of this function f, you will get the given problem. So what I want to take y plus z, x plus z, x plus y, and set that equal to f sub x, f sub y, f sub z. And in case you've forgotten, when I say f sub x, I mean the partial of f with respect to x. You can begin in any order you want. Keep in mind you're going to use all three of those to figure that out. So we start off with, so if I start in order, but you have to, if you take f sub x and set it equal y plus z, keep in mind when you are integrating, you're undoing a partial derivative with respect to x. That's not really how you write it, but sort of speak. And I would say f of x, y, z is actually y plus z. As far as x is concerned, that's a constant, right? Plus some function of y and z. Now comes the confusion. I'm going to go and review with you a little bit. If you were to integrate x squared dx, you would say that's x cubed over 3 plus c. What's c? C is a constant that when you take a derivative of this, will zero out. We'll think about it. If I had f equaling x into y plus z plus z cubed plus y to the 10th plus 50. If I take the partial with respect to x, wouldn't that be y plus z? And wouldn't all of these become a 0? So when I go back, I have to assume that there was a function of y and z in there. Now what? Now the goal, just like we did in 5a, I need to find c and I'm done. And that's why I said you're going to use all of these three. Now, if I take the partial of this f with respect to y, f sub y, that would be what? This is really xy plus xz plus g of yz. And if I take a derivative with respect to y, that's x, that zeroes out, plus the partial of g with respect to y. And what should that equal? Well, I know that this right here must equal the x plus z. And in this case, if I look at that, those cancel out. If g, the partial of g with respect to y is z, if I integrate, I'm undoing a partial derivative with respect to y. So g of yz would be zy plus a function of z, for the same analogy that we used before. So now I know this is zy plus h of z. That's my answer so far. I need to find what this is. And now I go for the last piece that I haven't used yet. I would say f sub z, the partial of this f with respect to z, that would be a 0 plus x plus y plus our natural derivative, and that should equal the x plus y. Now you're noticing a lot of things are canceling out. This only happens if you have a conservative vector field. And if you don't, you'll get extra terms. So my function that I found, f equal xy plus xz plus xy plus c. Now in the book, they set this c most of the time to equal to 0. You don't have to. Even better, a lot of times they write this as xy plus xz plus xy equal a c or 0, because that's how it's written in differential equations. You don't have to worry about any of that. You just have to find that f. And you could check, if you take the partial of this f, if you take the gradient of this f, what would that be? That would be y plus z. Something's not right. Oh, this was zy, guys. Say something. That was zy. So the partial with respect to x, that would be a y, okay? And the partial with respect to y, that would be x plus z. And the partial with respect to z, that would be x plus y. And you'll notice that's exactly what we started with. So I found a function f in which, when I apply the gradient on that f, I'll get the vector field. Another problem like this. Another problem is number 10. The same deal. I would like to find... My cat is going inside. I want to find a function f of x, y, z such that when you apply the gradient on it, you will get that vector field. So that means I am going to take y, the sine of z, x, the sine of z, x, y, the cosine of z, set that equal to this gradient, and figure out what that is. Now, I just gotta warn you, if you find a shortcut, that means this is conservative. It doesn't have to be conservative. And again, I could start in order. It doesn't matter which way you begin. You could say, well, the partial of f, I took a partial of this function with respect to x, and I got y, the sine of z. When I integrate and I'm undoing a partial derivative, f would be x times y sine of z plus a function of y and z. Find this function and you're done. And to do that, you need both of those. First, I could go in order. If I take a partial with respect to y of what I got, that would be x sine of z plus the partial of g with respect to y of yz. And that should equal, that's guaranteed to equal, and again, things cancel out nicely here because they're conservative. It doesn't have to be. So just a warning. If you find a shortcut, it doesn't always work. So g, when I undo a partial derivative, that would be a function of z, right? So now this is a function of z, and now if I take the partial with respect to z of what I got, if I take f sub z, that is xy, the cosine of z, plus the traditional derivative, that's going to equal the k component. I know I said that many times, I'm not going to stop. That only happens when you have a conservative vector field, and if you integrate, you get h to be some constant. Again, most books, f equal xy, the sine of z plus c. Most books set that equal to 0, or they even write this as xy, the sine of z equal to 0. Again, for differential equations, you don't have to worry about any of that. You just have to find me that equation.